So what are these atoms like? So after the proposal of this atomic theory, then people are, doing experiments and trying to investigate this. J.J. Thomson lived in the late 1800s, early 1900s. He discovered a smaller particle than the atom. It's called an electron. It's negatively charged. It's much, much smaller than the actual atom, also much lighter than the atom. And they found that it was present in everything. So the atom is still the smallest identifiable piece of an element. It's still the building block of all matter. But the atom itself is composed of different particles. And one of those particles is the electron. The fact that you can find electrons in all types of matter tells us it's a universal part of atoms. So then the question is, okay, there's electrons in the atoms. How is an atom put together? What does it look like? He proposed that the electrons, which were negatively charged, were held somehow in this sphere of positive charge that balanced the negative charge. This is called the plum pudding model. Anybody ever had plum pudding? I've read a lot of British mystery novels and stuff, so I've heard about plum pudding. But the British have different ideas about things. They call things different names than Americans do. The closest thing, or the thing you would most understand, it'd be like a blueberry muffin. So a blueberry muffin, you can probably picture that. There's the muffin part, and then there's blueberries kind of stuck throughout it, really quite randomly. And that's sort of what this idea was, that the electrons are like the blueberries in the muffin, and they're just kind of scattered around. They could tell that atoms themselves were neutral. So if the electron is in there and it's negative, there's got to be something else in there that's positive to make the overall thing neutral. So this was the idea. You got to start somewhere. So 1909, Ernest Rutherford was investigating this plum pudding model. If I remember correctly, he was actually a student of Thomson. He was not setting out to debunk Thomson's idea of the plum pudding model. He was actually trying to demonstrate that it was correct, but he did demonstrate that it was wrong. So this is the experiment he did. He had this source here that would shoot out alpha particles, which are very, very small particles. They're about the size of the smallest atom. And so we shoot these alpha particles out. They have positive charges. So he shot it at a very thin piece of gold foil, and then he had a detector, a circular detector around here, so he could tell what happened to those particles. Now, if you're shooting, say, baseballs at a brick wall, what do you expect the baseballs to do? Bounce back, right? Do you expect them to go through the wall? No. No, you don't. So what happened here is most of these particles did go straight through, and that's actually what they expected to happen. But some of them deflected back. This is a very, very thin piece of gold foil. It is not at all like a brick wall. It's really more like a volleyball net, and you're shooting airsoft pellets at it. Then you would expect them to go straight through, because in this electron here, in this model of the atom, there are these electrons, but the rest of this sphere of positive charge business, that was just like positive charge, some like ether or something. It wasn't actually solid. And so what they were expecting is that being a lot of stuff here, that it would go straight through. But some of them bounced back. So this is what they expected to happen. The alpha particles, they anticipated would go straight through. These electrons were really, really tiny, and so they didn't really expect that the electrons would have any effect on the path of the alpha particles. What happened, though, a lot of them did go through, but some of them bounced back. And Rutherford's reaction to this was, he said, this was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So imagine a large piece of tissue paper and taking a cannon with a 15-inch ball and shooting at the piece of paper. And it bounces off the piece of paper and hits you in the forehead. Would you be surprised? Yeah, you might be dead too, but you would expect it to go through, and that's what they expected, it to go through because these particles were too tiny. But they bounced back. So the plum pudding model is obviously, there's something wrong with it. So then we have to revise it, come up with a new model. That's what the scientific method does. So this led to the nuclear model of the atom, or the nuclear theory. And this says that most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. So if we look at this picture, this is an illustration of the nuclear model. Here we've got the nucleus in the center. That's where almost all the mass is and all the positive charge. So they're shooting positively charged alpha particles, and when it gets close to or hits this nucleus that's positively charged, positive charges and positive charges repel each other, and it'll bounce back. And it's very massive. So you hit it with that alpha particle, and it's not going to go anywhere. The particle bounces back. Most of the volume of the atom is empty space. And in that empty space, we have these tiny negatively charged electrons. They're dispersed. They're in there somehow. So that part of the plum pudding model was sort of correct. We get these negative charges sort of dispersed in this area. The difference is, instead of this large diffuse positive charge, all the positive charge and almost all the mass is focused in that nucleus. The number of negatively charged electrons on the outside of the nucleus is equal to the number of positive charges inside the nucleus. And we're kind of skipping over some of the history here. The positively charged particles in there are called protons. So negative electrons, positive protons, there's an equal number of them so that overall the atom is neutral. Further work on that nuclear theory showed that this nucleus not only has protons in it with positive charges, but it also has some other particles that are called neutrons. They're neutrons because they're neutral. They don't have a charge on them, but they are massive like the protons are, massive compared to the electrons. The dense nucleus makes up more than 99% of the mass of the atom, but occupies only a small fraction of the volume. And so this is kind of trippy when you start to think about it. I mean, you look at the desk that you've got your papers on, and it feels pretty solid, right? You don't want to try to do a karate chop and stick your hand through it because you're going to hurt your hand, right? It's solid. It's actually mostly empty space. Your hand is also mostly empty space. The thing is, the little bits of mass that are there are held together by very powerful forces, and so we can't have matter just passing through each other, but it does make all those science fiction ideas seem like, well, if we could just figure out exactly how to do it, maybe it would be possible. Just to give you kind of an idea of the size here, if the nucleus was the size of a pea, just a little green pea, and you stuck that on the center 50-yard line of a football field, the size of the atom as a sphere would stretch from end zone to end zone. All the mass of the atom is in that little tiny pea, and the rest of that volume has almost no mass in it. It's mostly empty. Little tiny electrons, about 2,000 times smaller than the nucleus, are in there, but really nothing else. So the nucleus is incredibly small. And it's incredibly dense. If you were able to take nuclei, just the nuclei without the extra space, and make them the size of a period on a printed page, little tiny period. If that was just nuclei, it would weigh millions of tons without all the empty space from the atoms. It's pretty crazy. So the electrons kind of distributed around here. They take up that space, but they don't have much mass. So they're a little bit like water droplets in a cloud or water droplets in the fog. So we have some pretty impressive fog around here in the winter. You go out in the fog and you can't see. You can't see across the street, right? You can't see through it. It kind of looks solid, and yet you can walk through it no problem, right? It's mostly empty space with these little tiny droplets of water that you can't actually just see with your eye, right? So that's a little bit what the electrons are like. And they kind of do behave like a cloud. Any questions?